Okay, I think that we can start. So welcome everyone to the webinar Total Common Water Vapor. This is the third and the last webinar on the use of in situ climate data arranged by the National Research Council in cooperation with the European Centre for Medium Range Weather Forecasts and the Copernicus Climate Change Service. I'm Monica Proto, technologist at the National Research Council, and I'm very pleased to welcome you and moderate this webinar. I'll spend just a few words about the purpose of the webinar and some technical indications. As mentioned before, this webinar is a part of a cycle of 3 webinars focused on the use of in situ climate data and to provide information on the use of them, on their measurement, and finally their application. A wide range of data and services have already been provided under the Copernicus contract for the implementation of the C3S Climate Data Store. So I would like to thank all participants for attending this Copernicus training activity. And I'm so honored to introduce Professor Jun Wang, who is the program manager for the New York State Mesonet and a research associate professor at the Department of Atmospheric and Environmental Sciences at State University of New York at Albany in the USA. Jun is an international leader in weather and climate observations and networks, surface and upper air instrumentation and data quality, and ground-based GNSS meteorology. She has been playing leadership roles in designing, implementing, and operating of 2 observation networks, the GRUA and NIST. She served as co-chair of GRUA Working Group until November 2022 and is currently chair of the expert team on upper air measurement for World Meteorological Organization. So I thank you, June, for your precious availability and for accepting our invitation to take part to this event. And I inform you that after the presentation, there will be the QA session, 30 minutes long. So I invite all participants who would like to submit their question to June, to the speaker, to write their question in the dedicated box on the right of the webinar panel. And finally, I want to remind you that the webinar is recorded and made available on the C3S webpage. I take also this opportunity to inform you that the webinar material will be made available on the C3S webpage. Once ready, I'll send you an email to all participants to inform you. Now I leave the floor to June. Thank you again. Please.
Okay. Thank you, Monica, for a great introduction, and thank you everybody for participating in this webinar, especially Friday afternoon. And thank you, Monica and her team for setting this up. And so let me try something I want to do. Okay, because I want to somehow see myself, but also see my screen. So hold on, sorry. All right, so today I'm going to talk about the total column water vapor for climate. I will focus on 2 things, measurement and applications. And so I will divide this talk into 3 parts. We will start with one motivation. Why do we want to study water vapor? Why do we want to measure water vapor? And then get into the measurements of the water vapor, especially for total column water vapor. And then focusing on the GNSS, total column water vapor measurements. How we do that, why do we do that, and what we can get out of that. And then I will end with 2 applications. One is long-term climate trend of the total column water vapor. And so one is extreme event using the GNSS total column water vapor. When I talk about the total column water vapor, I hope we all are on the same page. That's column integrated the water vapor in the atmosphere from the surface all the way to the top at the top of the atmosphere. Although it's dominated by the water vapor in the lower atmosphere. Sometimes people also call pressable water, also called integrated water vapor, IWV, PW. You will see in my talk, I kind of use different words, here and there, and hope you understand they all are the same thing. So let me start with the motivation. Hold on. I'm trying to organize two screens. Okay. Why do we want to study water vapor? How important is water vapor to the climate change? This is a summary from a frequently asked question in IPCC AR5. I have to mention, because I don't really know who you guys are, what are your backgrounds. Sometimes maybe I say something, give you something information, very simple, you already know. Maybe sometimes it's too complicated for you. Hopefully you can get the ideas. So why? Water vapor has the largest greenhouse effect, and it's controlled, it's mainly controlled by the air temperature. Air temperature decides how much water vapor the atmosphere can hold. It's not controlled by emission. And however, other greenhouse gases, primarily CO2, are necessary to sustain the presence of the water vapor. Why? That's because given our Earth, it has to have the CO2 maintain the temperature, and that temperature decide it's in the water vapor phase rather than solid ice, all in a liquid phase. We all know water has three phases. Now, water vapor is not a false thing. I want to mention that, but amplify the climate through feedback. Water vapor is a dynamic parameter, like what you see here in this cartoon. And so you get evaporation of the water from the ocean, from the land, get into the atmosphere, form the clouds, and precipitating to the ground or ocean. You finish the whole cycle. So it's a dynamic parameter through the precipitation, condensation. Normally in the air, it has a 10-day of lifetime. Water vapor is also a very important essential climate variable for extreme climate events such as drought and flooding. So regarding the extreme events, one of the things is, especially recent last few years, it has been in media a lot of times, it's about this atmospheric river. This is a cartoon from NOAA regarding atmospheric river. What is that? It's a very high concentration of water vapor, narrow band, and coming from the ocean, get into the land, especially along the mountain region, lifted and then cooled and forms clouds for heavy precipitation or heavy snowfall. This is a map of one atmospheric river event in 2009 over the Antarctic Ocean, and this get to the UK caused a very extreme precipitation flooding event. Here map showing those red circles are the most commonly occurrence of the atmospheric river over the globe. And then those shaded areas are the impacted area over land. As you can see, this is not a local phenomena rather than global phenomena. And it's not just over the west coast of the US, other regions too. And then move on to the measurement side. It's really challenging to measure water vapor because of its high temporal and spatial variabilities. Here is just a schematic diagram of the temperature, global mean temperature profile, solid line, dotted line, and the solid line is water vapor mixing ratio. If you look at the scale, it's a log scale. It's from the surface to, it's about 10 to 20 gram per kilogram. Then you get to the stratosphere. It's 4 order of magnitude of change for the water vapor in terms of vertically. Here is a total column water vapor, annual total column water vapor for 1992. As you can see in the tropics, it can be 50 millimeter. However, in the polar region, it's less than 4 millimeter. And then here is a time series of GPS total column water vapor from 1997 to 2006 at Miami Station. It's a 2-hourly resolution of data. First of all, you see a strong, it's dominated by seasonal variability. On the top of that, you see the day-to-day variability. If you zoomed in, you will see diurnal cycle again. Given this very large spatial and temporal variability, so it's really challenging to measure water vapor. And what do we have for sensing water vapor? Here is a cartoon summarize all of those available instruments. In the space, we have geostationary and polar orbiting satellite for total column water vapor measurement. And then in the lower orbiting, we have GPS satellite and GPS receivers. And on the ground, we have GPS receivers too. And those will be my focus in terms of water vapor measurements, especially ground-based GPS measurements. And then in the air, you also have weather balloon, radio sound, and you have commercial and research aircraft for water vapor measurements. On the ground, we have the surface humidity measurements for all of the ground-based surface network. Then we also have ground-based remote sensing, such as Raman LiDAR, microwave radiometer, water vapor dial. They all measure total column water vapor. So I am going to focus on the GNSS. Let me start it with some fundamental concept of the GNSS. We all use our cell phone, smartphone. And how does it work? What I show here is just from Wikipedia. Here is our Earth, and those big blue dots is our ground-based GPS receiver, and those small dots are the GNSS or GPS satellite. It used to be called GPS because it was started from US in 1970s. Right now, you have more than one type of the GNSS, GPS, GLONASS, others too. And so what you see here is your ground receiver in any time it will receive those black dots anywhere from 7 to 12 satellite, GPS satellite can see those. And those GPS satellites send clock information and position information to your ground-based GPS receiver. As you can see, from 1979 to 2014, the number of the GNSS satellite has been increasing dramatically, and that provides us opportunity for more applications. So we should know the GNSS, it's mainly for position purpose. In other words, for geodetic purpose, for survey purpose. That's why over the globe, you have everywhere, you have those ground-based GNSS receivers. I show few picture of them. There's different types, receivers, different types of dorms. You know, like in Hawaii, it's mainly for volcano monitoring, and other places for, you know, other geodetic purpose. And as a result, because of the geodetic applications, and we also see a lot of ground-based GNSS stations. Just to use the US as an example, you have SUMINET, you have Plate Boundary Observatory, and each state has their own curious stations just for survey purpose. And then you see globally, we have the International GNSS Service Network in Japan. Because of the earthquake risk, they have very, very dense GNSS networks, and then other regions too. Europe, as you can see, a lot of stations too. So let's get to, those are for the positions. Why are you talking about water vapor measurements using GNSS? What we are trying to do is try to turn the geodetic noise to meteorology signals. How does that work? Here's your ground-based GNSS receiver. Here's your GNSS satellite. Satellite send the signal to your receiver. However, this signal is delayed by the atmosphere, both ionosphere and troposphere. And the ground-based GNSS receiver are at least two frequency, L1, L2, and others too. And by using two frequency, you can remove the ionosphere delay. So the total delay is a combination of ionosphere and the troposphere delay. And remove the ionosphere delay, what you get is tropospheric delay. We normally call total tropospheric delay. And that delay is along that path. You can scale that to zenith direction. So it's called zenith tropospheric delay or zenith total delay. That's a combination of hydrostatic delay and wet delay, or dry delay or wet delay. The hydrostatic delay is mainly a function of the surface pressure, and then wet delay is a function, it depends on the atmospheric temperature and water vapor in the troposphere. If we know the water vapor weighted mean temperature in the atmosphere, we can get do an estimation of the total column water vapor in the atmosphere. So for the position purpose, people need to know this delay to get a better position estimate. But what we try to do is we know the position, how we can back up the total column water vapor, right? So this is the high-level summary of how we got the total column water vapor from ground-based GNSS receiver. And then let's look at a summary of all of the water vapor measurement technique, compare them in terms of the availability, temperature, and spatial resolutions, coverage, accuracy, and long-term stability. Why we talk about the long-term stability? Because this is for climate purpose. So I have here GNSS, radio sound, satellite, ground-based remote sensing, and I'm not going into the details, but I want to highlight what's special about GNSS. So GNSS, it's available under all weather conditions. It doesn't matter, it's rain or snow or clear sky or cloudy sky. It has a very high temporal resolution, basically it's continuously. Anywhere for GNSS PW products, anywhere from 5 minutes to 2 hourly. And it started in 1994. So we have data more than 25 years. And as I mentioned in the last slides, the stations, the networks, GNSS networks are expanding. And I think this is more than that. This is quite a while ago. I put this number there. It has a high accuracy because it's basically the reference measurements is the clock and the time and the position of the GNSS satellite. They are very accurate. It's traceable. And it has a long-term stability. So why do we care about those things for climate study? Here, it's why we want all weather condition, high temporal resolution for diurnal variation for climate extremes. And we want a high accuracy for validation of the other measurements, such as satellite water vapor measurements. We want a long-term stability for long-term water vapor climate trends. So that's why this has been a lot of efforts have been put into here, into the water vapor measurements, and I will focus on this. So let me move on to another topic. So in terms of water vapor measurements, it's in general, it's the measurement. Why do we care about uncertainty? This is a Guan concept that Guan has spent the last more than 10 years to work on the uncertainty estimate. So fundamentally, a measurement is you assign a numbers to an object or events, but a measurement includes three parts. It's your magnitude units and uncertainty. In other words, your measurement is a number plus minus your uncertainty. And in practically, this is a very simple example I used to teach measurement class. This is from my class. And so to tell you why we care about uncertainty, let's say a queen or king has a crown, and they give you George and Martha's task of to measure to determine whether this it's an 18 karat gold or cheaper ones, and what do you know is the density of gold and low. And here's what they measured, the value. Given those two numbers, it's really hard to decide whether they are gold or alone, right? If I tell you the uncertainty of both measurements, and then you will say, Martha did a great job. I would trust this measurement more than George's one. And based on Martha's measurement, I would say it's not really 18 karat gold. So how do we estimate the uncertainty for GNSS PW? And I already mentioned all of those things, how we derive the PW from the total troposphere delay. What we do is just using fundamental uncertainty propagation equations. This is something you might got from your measurement class or data analysis class. And then apply that to all of those equations, how we derive the PW. This is what we get. All of those things are summarized in Yin et al. 2016. We did this for Guan products, GNSS PW products. So it's an uncertainty as a function of your ZTD, your surface pressure, and other other variables, the PW magnitude too. In summary, it's the uncertainty is dominated by zenith tropospheric delay, zenith total delay, and the other constant, and your water vapor weighted mean temperature in the atmosphere. So we need to know the uncertainty of those variables too. And so in the end, what do we have right now for the GNSS PW products? I want to draw your attention to this really nice products from C3S. They have this on the website. This is the GNSS PW products from 1996 to current. It's an hourly resolution. It's a combination of the IGS stations and the European EPA stations, as you can see from this map. It's not just PW or PW variables. Every data point has uncertainty with that. They also have ZTD there. They also have reanalysis PW there. So if you want to do some studies on the water vapor or other related projects, please check out this website. It's very easy to download too. And then let me move on to my first applications. The GNSS PW4 trend and diurnal asymmetry study. This is a study my group did and published in Journal of Climate back in 2016. What we did is combine 2-hourly GPS PW data we developed quite a few years ago, and then PW from the homogenized radio sound data and microwave satellite microwave radiometer data over the ocean. We combine all those three together to create a global picture of PW products. And here, let me move on to a very simple motivation. Why do we care about long-term trends? What do we know right now? This is from the most recent IPCC report AR6. This shows you the monthly anomaly of the PW from 3 reanalysis products here and 1 merged products NVAP from Colorado State University, 2 satellite data. As you can see from this plot, overall, they agree with each other in terms of the trend, positive trend, and the interannual variabilities. However, you see back in 97, back to from 1980 to 99, even 1990, there are a lot of disagreement among different reanalyses, and look at the merged NVAP, that's kind of outline compared with others. Although most recently they kind of converge, there is still a lot of uncertainty with that. Let's look at the maps. This is from the DVAC Water Vapor Assessment Project. They look at the global map of the total column water vapor trend from 3 reanalysis, mirror, CFSR, ER interim, from 1988 to 2008. And then this is NVAP and 2 microwave satellite. The bottom line is they show some similarity in terms of the spatial variability, but the magnitude can be very different, and especially some of the regions like in South America and Africa regions. So, and then let's look at another thing is we know the temperature controls how much water the atmosphere can hold. Here is from IPCC AR5 in terms of the trend in lower troposphere temperature and trends in PW from all of those different climate models and 3 reanalysis here, 2 microwave satellite data. As you can see, they are quite different, especially climate models all over the places for both water vapor and tropospheric temperature. The reanalysis and the satellite, the temperature trends are pretty good, narrowed in this region, but water vapor can be very different, especially for the reanalysis. So we still have a lot of work to do. And then I already mentioned most of those. We also see in terms of how the water vapor trend vary with the temperature. There are different reasons for that. I will get into more details later on. So our main goal is what is the best estimate of the global PW trend? And global means both land and ocean, and its spatial variability and temporal variability. And then next, we really want to look at the interannual variability and trends, how that can be related to temperature trends, temperature changes, why. And the last one is very unique, it's diurnal variability of the PW trends. This can be only done using the GNSS measurements. So some summaries of this result. Here, let's first look at the global mean time series for both PW and surface air temperature, or surface sea surface temperature, and over the land, over the ocean. Here, the black line is from the homogenized radial sound data. The blue line is the surface temperature. The red line is from the GPS. And there, here, the blue line against the sea surface temperature. The black line is from the satellite data. A few main points. For both land and ocean, we saw positive trend. That means our Earth is getting more humid and warmer. And you see on the top of that trend, we see a lot of strong interannual variabilities. They are dominated by ENSO events. And also you can see the trend and the interannual variability of PW and temperature are well correlated for both land and ocean. And another thing I want to mention is if you look at the homogenized radial sound data and the GNSS, they agree with each other pretty well. Although starting from 2006, there's some disagreement here. So let's move on to a summary of the trend for PW surface temperature and their correlation. Some of the points already made from the map. Again, climate is getting warmer and humid, no matter whether it's short period of time, 95 to 2011 or 88 to 2011, they all are positive numbers for TS and PW. And you see the PW trends over the land. Those are the red, warm colors. They are much smaller than over ocean, those cold colors. This is what you expected because over the land, there are other process controls of water vapor, but over the ocean, it's mainly controlled by thermodynamic components. Otherwise, temperature is a main control for the PW. And you also see temperatures, same things, even much larger. It's a reverse. Over ocean, you get a much smaller trend because of heat storage over in the ocean, right? And very good correlations, however, much better correlations over ocean. Again, like I mentioned, it's mainly because over land, there are other processes controlling the water vapor in the atmosphere. Okay, let's look at the global map of the PW trend by using this merged data, 3 data sets. So over ocean from the microwave satellite data, over land from the radial sound, and those dots are GNSS measurements. First of all, you see a very unique spatial patterns over ocean, and they are consistent for different time period. I'm not going to dive into the details. It has something to do with the large scale atmospheric variabilities. And then you see over the land, GNSS and radial sound, they do agree with each other pretty well in terms of the trend. And those stable areas are statistical significant trend. You also see, we see kind of dominant of the cooler colors. That means positive trend for PW. And then the next thing is we really want to understand the trend to see how well the trend correlated with temperature. Normally people use this scaling ratio. It's the relative PW change with temperature. So you can derive this using your PW and surface or atmospheric temperature. So this is D log PW dTs. Why are we doing this? Fundamentally, theoretically, this is why. So we all know PW is an integration of specific humidity from the surface to the top of the atmosphere. Specific humidity Q is a function of relative humidity and saturation vapor pressure. Saturation vapor pressure is a function of a temperature. If we assuming relative humidity does not change with temperature, in other words, it's the trend does not change, long-term trend does not change with temperature. And this assumption is kind of valid based on the past study, although some recent study have questions about this. In that way, we will say the log Q is a function of the T. In the end, what you get is log PW variability with T is a function of the temperature. And if you use a global mean temperature based on this Clapeyron equation, you would get a 7% increase in water vapor per Kelvin of the temperature increase. So here's what we got from our data. So here is around this region, 6 to 9, around 7. But we can be very low number here over the land, a very high number over the ocean. And most of the region have the significant ratio for this number. But over ocean, we have larger than the 7% per Kelvin, but smaller over land, all right? This again is what I mentioned, is what controls the water vapor in the atmosphere. Fundamentally, it's different over land and over ocean. Next, we want to look at the diurnal cycle of the PW trend. This is only possible because of the high resolution of the GNSS data. The black line is, this is just one station. I show how we derive that, a 2-hourly diurnal cycle of the PW trend. Then we decompose that to a diurnal cycle. S1, blue line, S2, green line is a semi-diurnal cycle, and then put two together. So we apply this to all of those stations. This is what we get. This is the phase of the diurnal cycle of the PW trends. In other words, so when the PW is peaking. So here you see most of the stations peak at night. All right, and diurnal cycle dominates the subdaily variabilities, right? This is what we get from this. Let's look into more details what we get. Here's your nighttime PW trend compared with your daytime. Here you 1-to-1 on 1-to-1 line. So consistently, systematically, nighttime trend is larger than your daytime trend, all right, for all stations. And then let's look at the scaling ratio of PW with temperature. This is a histogram. The background, the green line is for daily average, the one, and then the red line is for the daytime, the blue line for the nighttime. Again, you see nighttime, you get the 7%, towards a larger value, around 7% per Kelvin. For daytime is much smaller than this number, right? Then how do we explain this? One of the things is we look at the correlations between PW and the temperature. So what you see here is for nighttime, here's for daytime. Several things you see for nighttime, you get this very high correlation between PW and temperature. But for nighttime, you do get some negative numbers, much smaller numbers than the nighttime. Here's your 1-to-1 line, right? Then what you see is there's no correlation between day and the night. That's because of the what controls the PW at during the daytime and nighttime. They are different processes. That's why they are not correlated. So this kind of implies, in terms of water vapor feedback, nighttime it's a much better indicator of water vapor than the daytime. So to summarize this, I'm not quite sure why it's paused. Monica, can you guys still see?
Yes, sure.
Why it says it's not paused?
Okay, no, I don't know.
Because I do get a window saying.
Okay, no, I can see your screen.
Okay, other people can see too? Because it says your screen sharing is now paused.
Okay. No, I can see, but you can try to turn off your sharing and then try again. So
okay,
you can see.
Let me advance that and to see.
I see the same screen.
Can you see change?
Yeah, I see the graph, so I can see still your slide in full screen.
Can you see the move? No?
No.
Okay, I think for some reason it paused. I kind of did not do anything. I'm not quite sure. Do you
Maybe
want
you can close the sharing and try again to open.
Okay, let me.
Okay, now
go to the slides where I am.
Pietro, dovresti dare i diritti a June, non a me.
Okay. Can you see my summary?
Yes, I can see.
Okay, everything's fine, right?
Yes.
Okay. All right. Summarize this part. We use the combined data sets to analyze the PW trend. We see the positive trend dominated over the globe with the larger trends over ocean than over land. And then we correlated the PW trend with the surface temperature, and the moistening trend is faster and closer to the closest Clapeyron expected value over ocean than over land. Only GNSS TCWV PW data allowed us to study diurnal cycle. What we found is at nighttime, the moistening rate is faster than during daytime and highly correlated with the temperature than the daytime. It's mainly due to other effects such as clouds. I did not really get into that. And then, so the results implies the relationship of nighttime PW and TS is better indicator of the water vapor feedback. Let me quickly move to the last applications. It's for extreme events, that is 2013 Colorado flood. And what's happening is the Colorado Boulder region got a continuous precipitation for almost a whole week. Heaviest rainfall is during those 2 days. Over 16 inches of the rainfall was recorded in Boulder, Colorado. and the annual average was 20 inches. As you can see, just within a 1 week, you almost get to your annual rainfall. You receive that much of the rain. And before that, the region experienced the wildfire extreme drought. That means very positive, that means it's prone to the mud flooding, and it caused more than 2 million damage, property damage, and claimed 8 lives. So what we did is combine the local ground-based GNSS stations and merge them together to get this 10-year time series of 2-hourly PW time series. Some of them are 30 minutes. And so we really want to understand the water vapor characteristics during this flood event. Why do we care? Why do we want to use GNSS rather than a radio sound? I already mentioned all of those. I won't want to mention. And another thing is you look at spatial coverage, much more station than radio sound stations. And this is what we say, just to use this time series as an example. The black line is from the 30 minutes GPS data for PW, and the red line is twice daily radio sound. This is the time during the flooding event. As you can see, PW, the GPS PW gives you a very detailed water vapor variability, but radio sound won't capture that. So that's why we need this high temporal resolution of the water vapor data. Here is a summary of the precipitation and PW variability during this 1 week. And when you see the black line is the PW, 30 minutes PW, and then the blue bars are precipitations. And then I have different line in terms of the media, climatology, medium 1 plus 1 standard deviation, all the way medium plus 3 standard deviation. So what you can see is precipitation started when the water vapor increased sharply to more than 2 standard deviation during this period of time. And then during this flooding event, most of the time, the water vapor PW maintains above the 3 times of standard deviation, and just to keep there. So that means it's precipitating. That means that there is a water vapor source keep, feeding this storm for those water vapor. And then, so this period of time, it's about 30 millimeter, and that's close to the saturation point of the whole atmosphere. We did look at the radio sound profile to see the saturation point. This 30 millimeter is saturated water vapor. So let's look at compare the climatology regarding this event, where we put this event. So what I put in here is climatology, either from a radio sound or 10-year GPS seasonal variability monthly mean. Here is for 2013 for September, that flooding event. That's above 99 percentile of climatology, in terms of how special this case is. Here I plotted we plotted the PDF of the PW for all 10 years and for September and also for 2013. What you can see is normally it's this normal distributions. However, during September of 2013, you get this bimodal distribution. Here's your normal environment for the September, later half of the September. Here's during flooding event. This is 95 percentile to 99 percentile. So not just a huge numbers, also the distribution changes for this event, right? So get to the question, where did we get so much water vapor? it's kind of synoptic conditions perfectly. It's not perfect, but it's too bad for the synoptic condition to get water vapor feeding from the Pacific and from Gulf of Mexico. Both regions had a warmer than normal sea surface temperature. That means more water vapor, more evaporation, more water vapor. And then your synoptic conditions, subtropical anticyclone here, cutoff low here, and blocking range. So that means all of the water vapor collected in this region. That's why we get so much water vapor, and that's why it stays there for dump all of those rains into that region. So summarize, GNSS, continuous GNSS measurements during the flood made it possible to study the detailed characteristics of the water vapor. And during the event, PW remained nearly saturated at 30 millimeter. And the PDFs of the PW also help us to understand the frequency distribution. Typically, it's not log normal, but here it's bimodal for that month. And then I also talk about why this we got so much water vapor because of the synoptic conditions. All right, I talk about those two case studies, but right now I want to combine those two together. So it's why it matters. You have a long-term trend, and then you have extreme events. Here's from IPCC AR6. What is this? Is precipitation changes per Celsius degree of warming, and for global time average 24-hour extreme rainfall event and 1 hour extreme rainfall event. And for observed change, different types of TCM and the regional climate model. I don't want to get into the details, but for all of them, you see as the climate is getting warming, no matter whether it's global time average, 24-hour extreme or 1 hour extreme, they all positively increase. That means heavy precipitation will generally become more frequent, and AR6 also show more intense with additional global warming, all right? So, and how does that precipitation intensity change with temperature? This is a nice study for DVAC in Netherlands. What they show is the intensity change with temperature for extreme cases, 99.9 percentile. That's focused on this one, extreme. And at temperature below 10 degrees, it follows this Clausius Clapeyron, 7% per Kelvin. However, above that, it's double that. And so it's the climate regime change in terms of how the precipitation intensity vary with temperature. Okay, does it have anything to do with the water vapor? I've been talking about how the water vapor is correlated with temperature. Here we talk about precipitation. And so this is a really nice study. They use hourly GNSS water vapor data over Japan. They look at water vapor change with the surface air temperature. And for different cases, 99 percentile. So if you look at the 99 percentile, below 14 Celsius, it's around the 7%. It's around the Clausius-Clapeyron equation. However, above that, it's much small variability. So this is the reverse of what we saw, the intensity, precipitation intensity. So this cannot explain what we saw from the last slides. Definitely this is a different region, but just qualitatively, we cannot explain why is that. This paper is nicely explained. We have to take into account, it's not just total column, it's in the free troposphere. I would encourage you to read this paper to learn more. So the question is, how does this PDF change in the future climate, right? As the climate is getting warmer, do we get more of this bimodal distribution? We move the mode to the more moisture environment without changing this distribution. So this all have implications on precipitation extreme events. There was a nice study by Chikola quite a few years ago. She did is using the climate model. Is black line is the first 25 years of, I cannot remember exactly the years. Anyway, this is the past, and the red line is in the future. As you can see, you see the distribution change. It's move. You get more of this very high PW values. That this is for Boulder. So that means it implies extreme PWV events are predicted to occur with much greater frequency in the future. Implies more, precipitation extremes. So summary for this part: as the climate get warmer, atmosphere can hold more water vapor. And past study already found that extreme precipitation intensity follows 2 times the closest collapse rate. Although we still try to understand that as the climate warms, the PDFs of the PWs also change. What's the implication on the event? And so then we really want to collocate the ground-based GNSS with precipitation measurements. I got the pose. Let me, because I only have my last slide.
I can see the slide is visible. So
okay, the take home message, you can see that, right?
Okay.
Can you see that?
I can see the summary.
Okay, that's why, because it paused. It's my last slides. Okay, and then you can see my everything, right?
Yes.
Let me go to last slide.
Okay.
Yeah. Take home message.
Okay.
Yeah, right. I'm not quite sure why I keep post that. Okay, take home message. I know I went through a lot of things. Those are things I want to deliver to you. PW or total column water vapor, I get used to call PW, sorry. It's an essential climate variable. It's challenging to accurately measure water vapor. However, GNSS derived PW has a high temporal resolution. It's available under all weather conditions. It's accurate and has a long-term stability. So it's great for climate studies. And I have shown you 2 examples of how the GNSS PW data are useful for long-term climate change and diurnal cycles and extreme events. And more applications still to come. I hope you guys are interested in this data and can do more. So again, I put the link for the data sets there. If you have any following question or comments after this webinar, you can drop me a message. My email is there. So that's all I want to say. Should I stop the screen share?
Okay, thank you. No, you can leave because there are some questions. So, no, it's better if, yes, you close your sharing so I can share my screen.
Okay, all right.
Thank you. Thank you, June. It is very impressive data, results, and example. Wonderful. Okay, now I'm ready to share my screen.
Okay.
Okay, but I can't. Yes, now.
Actually, I saw.
Okay.
Yeah.
So you can see my screen?
Yeah.
Okay.
Yeah.
So
Yeah.
the first question, does water column affect the dwelling shortwave radiation and soil temperature? If yes, how? By Al-Shibli.
Yeah, great question. And normally we say, well, water vapor is a greenhouse effect. It plays a very important role in terms of nighttime temperature. However, there are quite a few studies in terms of the water vapor in the atmosphere, and that absorb solar radiation. That's a direct impact. And there's an indirect impact is how much water vapor in the atmosphere affect how much clouds there, that would affect your shortwave radiation, right? So that's an indirect effect. In terms of the impact on soil temperature, that will be through the temperature. We know the soil temperature is coupled, especially topsoil layer is coupled with your air temperature. I would say that's how that would affect the soil temperature. I hope I answer your question.
Okay, thank you. The second one is by Telmo Vieira. Why atmosphere is getting drier in the equator or Pacific over those 3 decades?
Okay. Good
Maybe
question.
it refers to some
let me see.
figure. If you would like, we can change the sharing and you can.
Yeah, I know what you mean. I'm trying to remember.
Pietro, dai.
Yeah, I can share. I know. Yeah. It has something to do. Let me see what I can share. Screen. I know what you mean. I don't think I can share. But anyway, I know what you mean. Those positive, those negative trend, drying trend. This. Yeah, you are referring to those areas. This has something to do with, if you look at the temperature variabilities, temperature trend, I did not show here. And you do see that temperature trend corresponded pretty well. If I remember 5 years ago, we did this study. So in our paper, we kind of explained this whole thing. Also associated with the circulation changes. If you look at those are more subsidence areas. So I hope that's kind of what I remembered. Yeah, it's, as the climate getting warmer, those subsidence regions are getting more intense, and that means you're getting drier too. Okay, let me stop.
Thank you. There are other many questions. I try to collect them, just a few seconds, so we can see. Okay. Okay, Pietro, could you give me the rights? Okay, thank you.
Okay.
Well, can you see my screen?
Yes. Number 3, at what air pressure?
Yes. Okay.
Okay.
At what air pressure did you measure?
Yeah. It's a great question. For all networks where we want to derive the PW, and such as Gluon network, we strongly encourage the local institute to have surface air pressure measurements at the site, at the receiver level, because in that way you really get to your local surface pressure for your dry, your hydrostatic delay. So in terms of at what latitude, for our GNSS 2-hourly data, what we did is using the global surface surface data. So that's very high resolution. And then we interpolate if there's no collocated surface data. We did a kind of extrapolation and interpolation, horizontally extrapolation and vertically to the level, to the latitude. So in our in one of our paper 2007 for our GNSS 2-hourly data, we explain in details how we derive the local surface pressure for the PW estimate. And other people also use, reanalysis of the weather forecasting analysis for the surface pressure, which is GCM's old databases are in IGS 20, the IGS 20 frame, and all in old frames. I'm not quite sure what's the question about, which is GCM. That's the global climate model, or we call general circulation model or global circulation model. It's a climate model. And then in terms of, I know what you mean. In my presentation, I said the long-term stability for GNSS data. That's theoretically. In reality, because of the data processing and the instrument changes, your receiver, your radome, all of those things affect that. I don't know the details about C3S. It should be in the new frame. I cannot be sure. They have a very detailed document on their website.
Yes, maybe I can send you the link to the CDS, so you can see which are the data sets already published on the climate data store. Maybe it could be useful for checking this information.
Yeah. Okay, last question. It's a great question. I did not mention that. I said water vapor is not an emission. It's not more of affects the climate through feedback. It's not something like anthropogenic generated things. However, you are absolutely right regarding the water vapor coming as a result of those chemical physical interactions, like urban, especially urban climate. There are people studying those regarding the land cover changes and also man-made water vapor emission, how that affect. I would say at this stage, it's still not the dominated effect, but locally it might be.
Thank you, June. I check if there are any. Okay, there are some other. Can you see the screen of the questions, June, or not?
Hold on, let me see. Is that in chat?
Yeah, in questions box.
Questions box.
Okay. I take only
a
second to add here.
Yeah, I cannot see.
Right. Sorry,
Okay.
Okay, this is a comment for you. Now,
Yeah.
I move. Okay.
Okay. Yeah.
The other.
Yeah. Okay. Number 6.
Okay. Yes, number 6 and 7. And the last is a comment for you.
Okay. This Mexican Gulf Stream has changed, and another reason for climate change. Unfortunately, I don't know. I'm not an expert on that, but I think the most recent IPCC has a local regional climate since maybe there's some information. So sorry. And then number 7, calculate, we use pressure into ERA 5 and sea level. What do you use to be the best meteorology data to use for that? Yeah, for our study, we for pressure, we kind of explored the different things. That's in the end. I think for pressure, in the end, it's mainly your vertical location really really makes a difference. I hope you do the elevation adjustment from your sea level pressure, ERA 5 sea level pressure to your station height. And regarding TM, there are a lot of papers regarding which one to use. And in our 2005 paper, we investigate all kinds of different things. In the end, we use the reanalysis for that. I'm not up to date in terms of the most recent studies. I would say, based on our study, the reanalysis is really good, especially as the horizontal resolution is getting higher and higher for reanalysis, like ERA 5, and getting better and better for your station level of the data. And oh, thank you. Yeah, I hope you guys learned something. Sorry, I have a lot of things to show.
Yeah,
And,
no, thank you.
Yeah.
I agree with Sleepy, who has posted this comment for you, but it was very amazing and interesting. Thank you, June.
Thank you.
I think that there are no other questions. Check the last time. Okay, no, this is the last.
Okay.
Okay, thank you, June. Thank you all participants. And okay, see you next time.
See you. Bye, everybody.
Bye.